Hello students, welcome back to my YouTube channel Physics Club by Shakti sir. So in today's lecture I am going to carrying the Newton laws forward with new topics like the common forces in mechanics. You know, it's very important to solve the numericals if we are familiar with the common forces in mechanics like the weight, the normal reaction, friction, tension force, and the concept of equilibrium. So in this lecture I am going to discuss the concept of equilibrium with few numericals with the common forces. So stay tuned, and if you are new to my channel, please subscribe and like, share with your friends. Let's start. So common forces in mechanics. Common forces in mechanics. So we will discuss one by one briefly, because once we solve the numericals, we will every time we will repeat the concept of these common forces. So let's discuss weight. So weight of an object, it's quite easy concept. Let's say we have an object having mass m, okay, and this is some sort of table. So what is weight? Weight is nothing but a force. First of all, weight is a force, so it is a vector quantity, right? Sometimes we miscommunicate it with mass. Weight or mass, we considered it as equal terms, but in physics weight and mass are totally different terms. Weight is a force, but mass is a physical quantity, which is scalar quantity, but weight is a force with SI unit newtons. So let's say it has a mass. So the gravitational force of the earth is acting on this object downward with the force mg. That is the gravitational force, the magnitude of the gravitational force which is acting on this object toward the center of the earth. But as for a small surface, we are considering the earth to be flat, and this force is assumed to be acting towards the center of the earth under the condition that the force is a flat surface for this system. So this mg is nothing but the magnitude of the force acting towards the center of the earth. So weight, first of all, its first point is it is a force. Which force? It is a gravitational force. Gravitational force acting on the object by the earth towards the center of earth, right? So it means that this weight is a vector quantity. Vector. So with unit Newton. Newton is the unit. Okay, that's it. It's a very simple term. Weight. What is weight? It is the gravitational force acting on any object by the earth gravitational force towards the center of earth. So in this situation, I am just considering the gravitational force which is acting on this block, although the gravitational force is also acting on the table, but I am not considering the force acting on the table. Okay, and it is always downward. Second thing is, second force we are going to discuss is normal. Okay, normal reaction. There are few points regarding weight, that weight can change when we accelerate upward, when we accelerate downward in a lift, or when we at rest. So we will see those concepts even in the next lectures when it demands so. But right now, as I am trying to keep the concept as simple as possible. And what is weight? It is just the force, which is gravitational force acting by the earth toward the center of earth. Okay. the normal, or we can say normal reaction. Normal reaction. Oh, again, this is a surface and an object is placed on the surface, and I'm trying to draw, this is a surface. All right, this object is moving, let's say, in this direction with some acceleration a. So what's happening, the ground and the block both are in contact, right? The ground and the block both are in contact, so there is a contact force acting between these two. Contact force acting, so there is a contact force acting between these two, between the object and the ground. This contact force is subdivided into two parts. One is friction and one is normal reaction. Normal reaction. This normal reaction is at perpendicular to the surfaces in contact, as here is the surface of the object, here is the surface of the plane. So this normal reaction act perpendicular to the surfaces, perpendicular to the surfaces in contact. Surfaces in contact. Okay, and this friction force act along the surfaces in contact, act along the surfaces in contact. All right, but we are in this situation, we are just discussing about the normal reaction. So here what's happening, the ground, or we can say this platform is applying a normal reaction, or we can say, to make it more simple, let's discuss this. This is one surface, this is second surface, this is the surface of the block, this is the surface of the ground or platform or table, whatever it is on which the block is placed. So these two surfaces are in contact like this. Okay, so what's going on, the normal reaction acts perpendicular to this. The block apply the force on the platform and the platform is applying the force on the block. When the platform is applying the force on the block in the upward direction, so what I say, here is a force acting on the block in the upward direction, and this force, this is the normal reaction which is applied by the platform on the block. The same magnitude of force is applied by the block on the platform N2. As these two normal reactions are corresponding to the same common surfaces or same common platforms, same common layers, so what I can say, their magnitudes are equal. So we are going to write it something like this. The platform is applying the force on the block in the upward direction. Their magnitudes are equal like this, and this block is applying the normal reaction on the platform, something like this, and this must be perpendicular. These two forces must be perpendicular, and if the block is stationary, then this normal reaction passes through the center. I will discuss about it, that it passes through center of mass. Center of mass, as we don't know right now what is center of mass, So we can just say this vector, this force passes through the center of the object. So to make it simple, what is normal reaction? The normal reaction is nothing but the perpendicular force acting to the surfaces in contact. Here there are two surfaces in contact. One surface is from the block side and one surface is from the platform side. These two surfaces are in contact, something like this, and a normal reaction generate a contact due to contact force. Normal reaction generate which act perpendicular to these forces. Due to this normal reaction, the block is not coming down. We can say in our general language that the platform is supporting the block with a force of this. The platform is supporting the block by applying a force of normal reaction in the upward direction. Right? Clear? Okay. So keep in mind, normal reaction always act perpendicular to the surfaces. We can draw one more diagram regarding this. Something like this. Let's say we have a ball and there is a contact. Something like this. So what's going on? Normal reaction. There is a surfaces in contact. Here again the two objects are in contact. So, and this is the center. From this point a normal reaction act N1 in this direction perpendicular to the surfaces in contact, and from this side, from this contact, a normal force act N2 which is again the perpendicular, and both forces passing through the center of the object, center of the ball. Here N1 and N2 may be equal in magnitude, but we are not sure. That's why I am writing here N1 and N2. But in this situation, for single contact, the normal reactions are equal. If we consider just the normal reaction on the block, it is N. So it's a vice versa. As we know, the forces are always appear in pairs. So the platform is applying force on the block in the upward direction with the force N. So block is also applying a force on the platform in the downward direction with the same magnitude. As this is a common surface, so the normal reaction generates due to this common surface has equal magnitude. That's why if I write N1 and N2, so here N1 equals to N2 in magnitude, but directions are opposite. One direction is directed upward and the other one is directed downward, but they have equal magnitudes. But in these situations, the N1 or N2, their magnitude may be equal, but directions you can say they are at perpendicular with each other. Okay, so I hope you know, you have an idea what is normal reaction, what is weight. We will discuss about the friction with a complete chapter. We have a complete chapter on friction. There is a lot of problems, lot of concepts. So I am skipping this part, friction. Let's move to the next force, which is very useful for solving the numericals. That is tension. Tension force. Tension force is generated in the stretched string. We have a string, we stretch it, and due to stretched string, tension force is generated in the string. Let's see how this force behave. So tension force. So again, it is electromagnetic in nature. Electromagnetic in nature. And it come into existence in the stretched string. Stretched strings. Okay, let's see how. Let's say we have a hanger, we have a wire or string and a block having mass m. Simple example. Now what's going on? Due to this mass, this string is stretched, right? Okay, the gravitational force is acting on the block in the downward direction with force mg, that is weight of the block. But this block is at rest, it is not moving downward. Why it is not moving downward? Because the string is attached with it and string is holding the block with a force called tension force T. Few important points regarding the tension force are that tension force is always directed away from the contact. And you see, here is the contact at point A between the string and the block. So tension force is always directed away from the contacts. So I am writing here, it always directed away from the point of contacts, points of contacts. As here we can say there is also a contact, so here let's see T1 and it is directed downward, it is T2. Clear? This force generate when when the string is stretched. If the string is slack, something like this, then tension equals to 0. There is no force, no tension. But once the string is stretched, automatically develop in the this force automatically developed in the string. So slag. In slag situation, tension is 0. Stretch situation, tension generates. Okay, so I am saying this tension force is always acting up directed away from the point of contacts, as here at point A it is directed upward and at B it is directed downward in the string, inside the string. So there are few more things we need to know about the tension force. If the string is massless, if the string is massless, or we can say ideal string, massless or ideal string, then the tension remains same. In such situations, if I draw the diagram, M, downward force, mg, tension remains same if it is given that the string is ideal. And in most of the cases, if it is not given what is the nature of the string, we will by default we consider is as a massless string. But generally it is given in the numerical that the string has some mass or it is a massless. Okay. Second point we note about this is, let's say we have a situation something like this. Here is a block. Mass m. This is a pulley. Okay. Again, the gravitational force is acting downward, mg. If now we have pulley and string, two things. If pulley is ideal pulley means massless or frictionless, massless or frictionless, that's called ideal pulley. String is also ideal string. ideal string. Then what happen? Everywhere the magnitude of the tension remain equal, but keep in mind the directions. Here is a contact, so directed away from the contact. Here is a contact, so directed away from the contact, but magnitudes are equal. So in this situation it behave as internal force, so it will cancel each other. Here is a contact, so it is acted away from the contact. Here is a contact, so it is acted away from the contact. So we learned that when the string is ideal and the pulley is also ideal, then the magnitude of the tension in a string remain same. Okay, this is one situation. Now if the pulley has some mass or it has some friction, then the diagram will change. It means that the pulley is not now ideal. It has friction, or pulley has some mass. Now this single string now behave as two different strings. One from this to this, or we can say A to B and C to D. This is one part of the string or one string, and this is the other string. So the single string behave as two different strings. Why it's behave as two different strings? Due to the mass of the pulley. Now here I am writing T1 because still the string is ideal. It means that it is massless string. So when it's massless string, it is a massless string, the magnitude of the tension remains same. So C to D, string is massless, the magnitude of the tension remains same. String is massless, A to B, the magnitude of the tension remains same. So I'm writing T to T2. Okay. Third situation, when string has some mass, then what will happen? If the string has some mass, then everywhere the magnitude of the tension is different. Everywhere. So I'm drawing this diagram again. Here is a pulley, and this is the situation. Non-ideal string and non-ideal pulley, or string has mass, pulley has mass. String has mass. Non-ideal pulley. Now again there are 4 points: one contact, second contact, third contact, fourth contact. It has mass m due to gravitational force mg, that is the weight of the block, it's acting downward. At this point tension is in this direction, at this point tension is in this direction, at this point tension is in this direction, at this point tension is in this direction. But as string has some mass, pulley has some mass, that's why it is non-ideal. So tension everywhere has different magnitudes. So I am going to write T1, T2, T3 and T4. This is the situation. So I hope you understand how to denote the magnitudes of the tensions, where it is same everywhere and where the value of the tension in a string is different. It's totally depend either the string has mass or it is massless. One more diagram we can consider about the tension of the string, that's more simple diagram. Let's say we have a situation something like this. this is a string and here is the block M. The string has mass. So let's say this is the center C, this is A, this is B. So everywhere at point A the tension is T1, at this tension is T2, at this point tension is T3, and a gravitational force mg acts downward. You know the situations. Here the tension act upward direction. What about this situation? If I am going to ask what is the tension at point C, that is T2, so how we can calculate the value of T2? Let's say it has a mass of 2 kg, uniform mass distribution in the uniform mass distribution. In the string, and mass of the string is, let's say, 2 kg and its mass is, let's say, 4 kg. So if I am going to ask what is the tension T2, so firstly we need to concentrate on this word uniform mass distribution. As the mass is uniformly distributed and it has a 2 kg mass, it means that it is the center. So 1 kg mass is distributed in between A and C, and the other 1 kg mass is distributed between B and C. Okay. So the tension at point A, for the tension at point A, we will solve it something like this. T1, that is in the upward direction A, and it has a mass M, and a force is acting mg downward direction. The block is at rest. Block is at rest. What does it mean? It means that the total upward force equals to total downward force, and both the forces cancel each other. That's why the block is at rest. Getting it? So upward force equals to downward force. Upward force equals to downward force. What is the magnitude of the upward force? T1. What is the magnitude of the downward force? mg. So T1 is nothing but mg. What is the value of m? 4 kg. 4 g equals to 10. It's equals to 40 Newton is the magnitude of T1. This T1 comes out to be 40 Newton. Simple. Let's move. Calculate T2. How to calculate T2? So for T2, I am going to take this as system. So in this system, what is the value of the mass? 4 kg is the block mass and 1 kg due to string. So at C, so this is point C, tension force acting upward T2 and a mass of 5 kg acting downward 5 kg. 4 kg due to this block and 1 kg due to this string. So combined system has total mass of 5 kg. So this is the point C, the point C. Again, the system, this system is at rest. It means that at point C, the total upward force equals to total downward force. So the total upward force at point C is T2 and the total downward force is 5g mg, that is the gravitational force. So upward force equals to T2 and downward force equals to 5g. Let's put the value of 5 into g equals to 10. It comes out to be 50 Newton. Okay, so T2 is 50 Newton. Again, in the same manner, we are going to calculate the value of T3 at point B. When we consider at point B, the system has total mass of 6 kg, 4 kg due to block and 2 kg of the string. So here the tension T3 equals to 6G. So T3 equals to 6G equals to 10. So 60 Newton is the tension at point B. So I hope you understand how to analyze a string having some mass. And here the mass is uniformly distributed. There are situations, there are numerical asked in the examination when string has variable mass in some particular order. So we will tackle those numericals too, but here I am just giving you the brief introduction how to handle the tension, how to how to represent the forces like the gravitational force, the normal reaction and the tension force. Okay. So let's move towards the equilibrium part of this lecture. So equilibrium. So in simple terms, we can say a body is in equilibrium, a particle is in equilibrium when total external force acting on that particle is zero. In mechanics, or we can say in this part of Newton laws, equilibrium is nothing but if the net force, net external force acting on the particle is zero, then we can say the particle is in equilibrium. That means if it is at rest, will remain at rest, or if it is moving in uniform motion, it will remain in uniform motion. That is why, because the total external force acting, this is the symbol of total summation. So if total external force acting on the particle is zero, then the particle is in equilibrium. Then the particle is in equilibrium. Here I am just saying the total external force, but there when we move towards rotational mechanics, there is one more term, that is the total external torque acting on the system is zero, because equilibrium, here it is the translational equilibrium, there is one more term, that is the rotational equilibrium. So in Newton laws, we are not considering the rotational equilibrium, we are just considering the translational equilibrium. So for the translational equilibrium, this is the simple condition, the total external force acting on the system is zero, then the particle is in equilibrium, that is it will remain at rest if it is at rest. Okay. So this is the situation of equilibrium, the block is in equilibrium, right, it is at rest. It means that the total external forces acting on the block is zero. So there are two forces acting on the block, one is downward direction, that is mg, gravitational force, if m is the mass of the block, and the other one is tension due to string, which acts in the upward direction. So it is in equilibrium. Okay, so we can say the total external forces acting on the system is zero. It is acting upward direction. If we take upward direction as positive, so this force can be taken as positive, this force can be taken as negative. This is the net external force, or more simplicity we can say something like this, this force is positive acting upward direction, this force must be negative acting downward direction, and the sum of these all the forces acting on the block or on the system must be zero. So when we solve this, T minus mg equals to 0, so T equals to mg. That's why in simple situations we can simply say the total upward force equals to total downward force. Why? Because the system is in is at rest, it is not moving. Okay, so let's solve one more numerical, one more example. Let's say we have a situation something like this, and here is a block having mass 30 kg. So there are 3 strings. This angle is, let's say, 37 degree. This is normal. So the question is, find the tensions in the string. So T1, let's say here, T2 here, T3 in this string. To find the values of T1, T2 and T3. How we can solve this? Simple, apply the concept of equilibrium. This block is at rest. It means that the total downward force acting on the block, that is 30 mg, is equals to the total upward force acting, that is T3. So T3 is quite easy to solve. T3 equals to 30 g. This is the value of T3. Okay. Here I am going to resolve the forces, because this tension at this point has some angle. So this is a point of contact. So we know that now the tension force always act away from the contact. Here is a point of contact. That's why T2 act in this direction, T3 away from the contact, T1 away from the contact. Okay. So we are going to resolve the value of T2. If this is 37 degree, this is also 37 degree. So in this direction, it is T2 cos of 37 degree, and in the upward direction, it is T2 sine of 37 degree. So we know the value of T3. Okay, we are just going to solve the value of T1 and T2. So at this point, let's say its name A. So this is point A. The upward force acting on point A is T2 sine of 37. The downward force acting at point A is T3. Point A is at rest. It means that total upward force equals to total downward force. So we get the equation T2 sine of 37 degree equals to T3. We know the value of T3. It is 30 G, or we can say 30 into 10, 300 Newton. Okay. Sine of 37. We know how to solve this. Sine of 37. So this is the ideal triangle. This is a right angle triangle. This angle is 37. This is 3, 4, 5. Right angle triangle. So from this triangle, the sine of 37 is equal to perpendicular upon hypotenuse. Sine value 3 by 5. So T2 multiply 3 by 5 equals to T3. T3 equals to 300 Newton. When we solve this, we get T2 equals to 500 Newton. Okay. So here T3 equals to 300 Newton. T2 equals to 500 Newton. Now just T1 is left. Again, at point A, horizontal forces. Let's consider horizontal forces. T2 cos of 37 towards the right side and T1 towards the left side. T1 is acting towards the left side. Again, the point A is at rest. So this force must be equal to T1. So we will equate these two forces and solve for T1. Let's solve for T1. What's the value of T1? So T1 comes out to be T1 equals to T2 cos of 37 degree. T1 equals to T2 cos of 37 degree, and from this triangle the value of cos of 37 degree is equal to 4 by 5. So T1 equals to T2, T2 equals to 500 Newton, 500 Newton and 4 by 5. 5 term cancel each other. So it is become 100 into 4, 400 Newton. So T1 equals to 400. In this way, with this very fundamental numerical, with this very simple example, just by resolving the terms and directing in the particular fashion in which the tensions are directed, and using the concept of equilibrium, we solve this numerical, the value of T1, T2 and T3. It's quite easy, but if you are new in the 11th class, it's not easy. Okay, so there is one more concept in equilibrium, that is Lami's theorem. What does Lami's theorem says? Lami's theorem. It says that if there are three concurrent forces acting on a particle, let's say this is force F1, this is force F2 and this is force F3 acting on a particle, and the particle is in equilibrium due to these forces. Due to these three forces, the particle is in equilibrium. Okay, this particle is in equilibrium and three forces are acting with some angles. So this is F1. So opposite to F1, this angle, we are taking this angle alpha. Opposite to F2, this angle, we are taking this angle beta, and exactly opposite to F3, this angle, we are taking this gamma. So the expression of Lami's theorem is F1 divided by, this is the magnitude of F1 divided by sine of alpha, the angle which is just opposite to F1, sine of alpha, is equals to magnitude of F2 sine of beta and magnitude of F3 divided by sine of gamma. Keep in mind the alpha, beta and gamma, the placement of alpha, beta and gamma. The alpha is just directly opposite to F1, the beta is just directly opposite to F2 and the gamma is just directly opposite to F3. So this is the expression. Here again we have three forces. If we know the value of alpha, beta and gamma, we can even apply the Lami's theorem to solve this numerical. You can try this numerical, right, with the help of Lami's theorem. Okay, now if we have more than three forces acting on the particle and the particle is in equilibrium, so this is a very important point. Firstly, we need to know the concurrent forces. Concurrent forces are, these three forces are concurrent forces. Concurrent forces are those which are acting at a particular point. These, all the three forces are acting on this particle on a particular point. So these forces are known as concurrent forces. Now I am saying if there are more than three forces or more than three coplanar forces, if there are more than three coplanar forces, acting on a particle, and the particle is in equilibrium, and the particle is in equilibrium, then in such situations keep in mind if there are more than 3 forces, and those forces should be coplanar. It means in the same plane. Like these 3 forces are in the same plane, as I am drawing these 3 forces on the board. So these 3 forces are coplanar forces. In such situations, what we need to do, we need to resolve all the 3 forces along 2 perpendicular axes. Then resolve the forces along 2 mutually perpendicular axes. Mutually perpendicular axis, and then apply the concept net force along the x-axis. This is the sum of the net force along the x-axis, put equals to 0, and sum of all the forces towards the other perpendicular axis, 2 mutual perpendicular axes. One is x-axis, the other one is y-axis. So all the forces, the sum of all the forces along the x-axis, put equals to 0. The sum of all the forces along the y-axis, put that to be 0. So due to this concept, we can handle the coplanar forces which are more than 4 in the numerical. Now the same point can be extended if the forces are non-coplanar. This is the coplanar condition. If the forces are non-coplanar, then again resolve all the forces into 3 mutually perpendicular axes. For coplanar forces, just resolve along 2 mutually perpendicular axes. This is 2 mutual perpendicular axes. One is y-axis, one is x-axis. If the forces are non-coplanar, the next point, I am discussing the next point. If the forces are non-coplanar, then we will consider 3 mutually perpendicular axes, and with these 2 situations, we are also writing the third one, that is the sigma force of z-axis equals to 0. So these 2 plus this one. This situation arises when we have non-coplanar forces. If we have just coplanar forces, simply 2 mutually perpendicular axes are sufficient to solve the numerical. But for non-coplanar forces, we need to carry the 3 mutually perpendicular axes, and all the forces along x-axis put equals to 0, forces along y-axis put equals to 0. The sum of the forces along the z-axis too, we need to equate equals to 0. So in this way, we can handle the concept of equilibrium. There are so many numerical examples, and there is no way to get the confidence or to solve all the numericals in one lecture. So I am just concluding my lecture here with these important points, with Lami's theorem, with the concept of equilibrium, with the concept of weight, normal reaction, tension. See you in the next lecture. We will elaborate these concepts in the next lecture with so many important, so many beautiful diagrams of mechanics, and we will solve the numericals. Wish you all the best. Stay tuned with physics. Stay tuned with my YouTube channel, Physics Club by Shakti Sir, and do subscribe my channel, share with your friends, and like it. Bye bye.